Okay, so yeah, I guess I'll get started. So hopefully you guys recognize this equation up here, right? I've been talking to you guys for a couple weeks now about these diffusive measurements, and they always have this form, right, where you get Wiener records for your outcomes. My favorite example again is if you have a spin system, you can couple polarizations to it. This is the hardest example. We're going to be doing 4 much easier examples today and maybe Monday. And the point was, if this thing has a spin, if these polarizations are moving up to the right and back, so this is a 3-dimensional axis, right? So this is orthogonal to these two. Yeah. Then, yeah, what you read off is this. How much the polarization rotates. And it only rotates a little bit. And then these records are, say, dw sub tx, dw sub ty, dw sub tz. Okay. And they all look like something, okay, for as long as you measure.
That's the trace of the total transmitted amplitude.
The trace, you said trace.
Yeah, maybe just let me get the y-axis there is...
The integral of these guys, yeah, because if I just drew dw, it looks like it's kind of easier to look at if you do the integrated one, because it's going up and down. Yeah, okay.
The degree of freedom that corresponds to like what you're measuring is like
the rotated polarization. It's the electric field in this direction, yeah. Which should be 0 if this thing is never rotated.
Hang on. You have 3 beams.
Yep.
And for take the beam that's going to the right on board. Okay. So then we call the right on board as the x-axis in this Cartesian space.
Sure.
You're now measuring the longitudinal electric field along that x-axis, or
No. The other transverse electric field.
Transverse to the direction of motion is what you're measuring for each of these guys.
Yeah, both of these are definitely transverse to the direction of motion. And it was prepared, say, in this direction. It's propagating in z. And it rotates according to how much spin component this has.
You're measuring it back in the original axis and seeing how much is it rotating. That's the idea.
Yeah. So this is vacuum, like the
There's nothing there.
exactly. Yeah. So that's the 0 state we've had in all our Krauss operators.
And would it still function? Would you still have like a trace?
Yeah, absolutely. It wouldn't just read 0 because this is a quantum vacuum. It would fluctuate. Yeah.
But it would be kind of wandering around 0 with a certain...
Yeah, that's where it gets so tricky. Yeah, you get what you get, and in my point of view, you can't really see you can't see any trends until you add it all up.
Sure. Yeah. But if we do add up, like we integrate, if there's nothing in the...
Oh, yeah.
What does that integral of dw look like?
Yeah, it would still fluctuate, but I suppose, it would just be around 0.
So then in a long time, that integral goes to 0.
Yeah. That's right. Yeah, all of those should just fall out in the examples we're doing too. You'll see exactly what you might expect to see. Okay, so the main thing I wanted to point out is you get n, so this is a sum over n different measurements. You get n sequences of Wiener increments. That is the raw data. But of course, how do you put that together into something meaningful? That's the whole point of this time-ordered exponential. Okay, so of course the first example to do is L is just a single Hermitian observable. Okay. So parenthesis just means sequence of things. So I'm going to make X Hermitian. Oh no.
You're going to need to choose another piece of chalk because I can't see it at all.
Jesus.
Or is it a blackboard maybe? Yeah, blackboard. It's old, it's rusted too.
I have a bunch of Hagoromo chalks in my office, and I'm on the 4th floor. Oh, is that better?
It's the lighting. It's in shadow. It's in shadow.
Jeez. Okay. Let me just experiment for a moment. Interesting.
Too smooth, so it doesn't pick up the truth.
Yeah, I see that. For some reason up here, it doesn't. Huh.
Yeah, it's because the chalk, when you use it on the blackboard, it wears away the surface of the blackboard. You do that for years, you end up with the blackboard
Wow.
too smooth to hold the chalk. So they have to be sandblasted with a fresh surface.
I'm going to move up to see better, but for the sake of the recording.
Yeah. I'm going to just start midway. Yeah. Okay.
It's certainly more visible if you lie below the shadow.
Yeah, I see. Okay. So, gosh. Example 1. Okay, so L is a single observable. So, hopefully you can see, right? If X is just a single Hermitian observable, then QL, that's just X squared, because X dagger is equal to X. By assumption. Okay. And so the time-ordered exponential actually, everything commutes. So it's just a regular exponential. Okay. So okay, so we still get our Wiener measure. But, But then the time-ordered exponential doesn't do anything. So I'm going to write that out then as L dot root kappa, and then this integral is really just here now. Okay. And then the integral over time of dt is just t. Oh, and I should just put an x here. Sorry. Okay, so that's the easy part. And now I'm going to do something a little interesting. But do you guys see what I've done here? I guess I shouldn't write a vector anymore. There's just one dw. Sorry. Okay. We're just doing one measurement of x. So do you guys see how this is just a special case of that? I don't need vectors here. Okay. So the tricky part is actually seeing that, well, as you can see, right, the Krauss operator actually is only different depending on what this thing evaluates to, right? If I get a different measurement record, if this part is the same, then the Krauss operator is the same, only up to a weight. Okay. So we actually need to collect all of the Krauss operators that are equal. Okay. And this is the interesting part. This is the simplest case of the Feynman-Koch formula. So you might have remembered how I was collecting the binomials. This is the continuous variable analog. Okay. So I'm going to define. Okay. Well, first I need to choose how low I need to go. I'm going to go that low. Okay. So I'm going to define the operation. Oof. This guy's going to have hair. goodness. Okay, I need to be lower. That's much better. So I'm going to define a Krauss operator that just depends on a single variable I'm going to call omega t. Okay? And this is going to be the sum over all Krauss operators. Of different paths. Okay, but I'm only going to sum over those.
Your calgraphic code notation was to turn the cross operator into an element of an instrument.
Yeah.
So you're actually summing over elements of the instrument.
Yes, indeed.
Because it'd be different to take some of the cross operators and then turn it into an element of an
Absolutely.
instrument.
Yeah. Good. Okay, so does everybody understand the notation I'm using? I'm summing over all paths whose sum is WT. Okay. All right, so
As a cartoon, I can take sort of the endpoint of a trace. Like it's on the x-axis, t minus is your capital T minus is your endpoint. I can write all the traces that sort of end at a certain.
yes, exactly.
Those are all the ones that appear on this one. If they end at a different height, those are all the ones that appear on another.
Exactly. Yeah. So maybe I'll draw that then. All of them start from 0, and if I say here's WT, yeah, there's going to be.
The x-axis point is capital T sub minus.
Capital.
0 to capital T sub
Oh, sure. Yes, absolutely. Yeah. Great. All right. So hopefully you guys can see this is just integral WT equals 0 to t dWt. Then this Wiener path measure. Okay. And then, of course, this thing sort of by construction is such that all the selective instrument elements are the same. X root kappa W sub t minus x squared kappa t. And let's try to fit them up there. Okay. Okay, so what I'm going to show is that this thing well, we need to know what this is, right? Yeah. I'm going to, oh, you want to look a little more?
There shouldn't be a vector on the building image.
No, there should not be.
And
Just a knee jerk.
capital T in the upper bound, again, that's T minus.
Should be T minus, yeah.
The one in the interval on BW is 0 to T. We're talking about the same capital T that appears in the left-hand side of the equation.
Yes.
Krauss operator curve.
Yeah, again, all the intervals go like this. And if there's T over dt of them, if this is 0, then the last interval, these are T and T minus. Yeah. Are you happy? Did I address your... Yeah, it's one of those details where, like, you know. Okay. Okay, so now I'm just going to experiment with the next board for a second. Just give me a second. Oh, that's much nicer. Can you see this? Yeah.
Move to the right as well, leave the one that you just wrote on.
Mm-hmm.
Yeah.
And probably, Yeah, of course.
copy on my phone.
I'm now thinking that the backmost board is the best one. I might just skip the middle board. Let me just
I'll take on the picture then you can.
take your time. I'm just gonna. Okay, that one's pretty nice. Oh, but then the middle one doesn't. That was pretty nice too. Okay, so that front one is the worst.
Probably the one that gets the most
Right.
use.
Right here, it's the top that's better than the bottom. Okay. Let me just make a decision. I don't know what I'm going to do on this side yet. Okay. So right now, we just want to calculate what this is. So I'm going to just rewrite it. Okay, so again, we want to know what is this guy. Ah, no vector, no vector. Okay. So the first thing I'm going to do is I'm going to insert a delta. Can everybody see what I just did? So I'm now, this can get, yeah. I just inserted a 1, basically. Okay, and so then I'm going to move this guy over here. Okay. Oh, okay. Let me do it better. Sorry.
Equal to the last expression we had on the previous one.
Let me, I'm not doing it very well. Okay. So this is the thing we had on the previous board, right? And this is equal to an integral without this constraint. And then I can enforce the constraint with a delta instead. I think that makes more sense. Okay, are you guys happier? So what I just did is I moved the constraint to here. Okay, so now I have a delta that's enforcing the constraint. Okay, so then I'm going to take this guy out. I'll move it just over here. So I'm just going to take out the dWt, and then I'm going to define the rest of it as dt of wt. Okay. So just to be clear, I've turned the problem now into calculating a function, and now I'm gonna stop calling it wt and just call it d mu dw 0t delta of x. Okay, so I just changed the variable of the function to x because once I make this time dependence explicit, to me it's a little confusing to have a wt here. So I'm just replacing the argument of the function now with x. So maybe to be a little clearer, because this part can get a little subtle, Like when you look at this, you might think of WT as defined as this functional, right? But I'm actually now thinking of it as a constraint, right? And so I'm loosening up WT now into a random variable, a non-fluctuating random variable, okay? But then I'm thinking about the rest as now a distribution function in that random variable. Okay? It's non-fluctuating relative to the path, right, because of this. But then somehow when you take this part out, now it is fluctuating again. Okay, so we want to know what that is. Okay. Okay, so it's not hard to get. I'll move over. I'll start backwards since this is a good board. Okay, so basically all you do is think about what is dt plus dt. Okay, that's all we're going to do. So I feel like I could actually move over here. That'd be just fine. Okay, never mind, change of plans. Okay, so what is t plus dt? Basically, we're going to show that dt of x solves the heat equation. Okay, so this guy, well, the first thing I'm going to do, of course, I can just replace all these with t plus dt's. But then I'm going to write the Wiener measure as the measure for dWt times the rest of the Wiener measure. Does everybody see what I did there? So this is, in fact, just the Wiener measure for all paths up to t plus dt. And then I can pluck off, because this is always just a product of all the dw's. And then, meanwhile, in this delta, right, I've got wt, dwt, and I can pluck him off of the last bit of the integral. Great. So then the thing to notice, right, is if, so I'm going to put an integral over here. You know, there's a ton of integrals, right? So the thing to notice is that this, in the path integral, is just dt. Yeah. So these path integrals are like infinitely many integrals, 1 over dw0, 1 over dw dt, etc. Is that like, so like when I write this, this is technically integral d mu of dwt minus integral d mu dwt minus dt all the way down to integral dw0. Okay. So this is just a bunch of independent increments. Great, so then I pluck that off. Similarly, I plucked off the dwt in the integral. And then observe that this thing in here is in fact just dt of x, but x minus dwt. Does that look good? So this is an example of what's called a Chapman-Kolmogorov equation. Okay. interested? Okay, so all that's left is to notice that this, well, I can write it as a translation. Right, so I can write this instead as e to the minus dwt ddx, or I should write partial derivatives. Okay, does everybody believe that? I just pulled out this translation and assumed analyticity. Okay. What do you think, Ela? Yeah? Excuse me. Okay, and then, well, what is that? That is just, notice, right, there's no dw in this part anymore, right? There's just a dw right here. Okay, so that means I can actually just do this integral. And what is it? It's, so dwt is a zero mean random variable, Gaussian random variable. So this is, in fact, just e to the minus, or sorry, e to a half dwt squared d2 dx of dt of x. Okay. Because this is just stuff that has nothing to do with dw. Yeah. All right, and where now this angle bracket means averaging against this kind of measure. Okay. So of course, your knee-jerk response might be, ooh, please forgive me. Oh, no, that's all fine. Okay.
I guess the last thing here, like the du, it's like a Gaussian dw, so you're like completing square, and that's great.
Yeah, this is the usual. Yep. So this is something I just know off the back of my hand. But indeed, it always involves completing the square. Alrighty. So, well, what is that? So I guess I have to continue here. Okay, so that means dt plus dt of x. Yeah, this is one of those things that's a monster to narrate, right? I keep saying dt, 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 dt. So I'm so sorry. So this is 1 plus half. So hopefully you recognize this thing as dt, right? That's the mean of a standard Wiener increment, the variance of a standard Wiener increment. Oh, Gesundheit. Okay, so here I've just expanded the exponential to dt. I feel like I lost a kappa at some point. I don't know what happened. I lost a kappa at some point. Oh, no, I didn't. It's fine. Okay. All right. So is everybody happy with this? I just expanded the exponential. Rob, I'm so sorry to make you squint. So this is just me, right? This thing can be expanded as 1 plus this little bit. Okay. So once you're there, hopefully you can see that I can move the dt over. So I'll just do that. dt plus dt of x minus dt of x divided by dt is half the Laplacian. Okay, hopefully you guys can recognize on the left we have a time derivative, right? I guess I should write it big T. It's more conventional since I called the final time big T. Okay. So maybe I'll okay. So this is the heat equation.
Put the big T on the right-hand side as well. Yes.
Oh, yes. Absolutely. Have I been? Yeah. Equation. Or more generally, right, special case, invariant. So this thing has two different names in general. It's either called a Kolmogorov forward equation, i.e., or Fokker-Planck equation. Okay. So then I'll leave it for you guys to check. But if I tell you that d0 of x is delta of x, so what does this mean? It means that the zero time instrument has only identity Krauss operators. Right, if we go back to, oh gosh, how is that even obvious? Yeah, I guess it's the middle one. Right, so if I go all the way back to big T equals 0, right, and I tell you, so this is 0, and the only thing that's left is what is this x, right? And if I say that x is equal to 0 at t equals 0, that means that all my Krauss operators are identity, okay, at t equals 0.
That's clear. Okay. I just wanted to note something that could be a potential confusion for anybody watching it, that I think you double used x, because you at some point you introduced x as a shorthand for dw. But here, x is playing a totally different role.
No, x was never shorthand for dw. X was shorthand for w.
W, yes.
Okay, right.
Where's that show?
Must have been.
There, x minus. So you're saying, yeah, x is just w sub t.
Yeah.
But on the previous board, x was like poly x with polarization, right?
Ah, it was the observable. Oh God, yeah. Right.
I just wanted to flag the fact that, I don't know, if you put a tilde on this x or something,
Yeah.
but you're now asking us to think about the x equal to 0 case, but that's not the observable.
Absolutely. Yeah, yeah. I was previously I put serifs on my operator x's, so I should just do that. So just to recap, yeah. Thank you. I mean, my little x's kind of look different from my big x's, but yeah. Okay, so those are all the observable x's. And, oh gosh, yeah. Thank you. Thank you. Okay, so I think my observable x's only made it on this board. Is that right? Yeah, and so then by the time I moved here, I wasn't even thinking about the Krauss operator anymore. Yeah. These are all distribution functions. Yeah. And great. Okay, so all of these are little x's. which are single real random variable. Alrighty, so if I give you this initial condition for the heat equation, then the solution to it is the famous Gaussian, right? dt of x is 1 over square root 2 pi t e to the minus x squared over 2t. Okay, this is what's called the Fourier kernel. Are people familiar with this? This is basically saying x is a random variable whose variance goes as time, which is
That's the unique solution to the heat equation for that boundary.
for the delta boundary condition. Yep. Yep. You could call this the Green's function of the heat equation. Yep. Okay, so I think what I'm going to do, since these are the two nicest boards, is just stick to these two boards. Yeah. That means I'm going to erase this.
Where you could use that, pull that, and swap the other one. Or does the other one not swap?
The problem is, so this one's okay in the middle. Yeah, the one I just drew on is much scratchier than these two. But I suppose I could have started with that one. It would have been a little better. Oops. Okay, so I'll use this one.
You don't need to refer to the board that's behind it.
Yeah. Okay. Yeah, I'm going to avoid that one and then the middle one over there. Yeah. Okay, so what did I just show? I just showed that omega of Wt is actually equal to this heat kernel. Okay, so does everybody see? I'm going to put parenthesis Wt in the measure d so that this isn't confused with the final Wiener increment. Right. You remember how, I think, yeah, you guys didn't get confused about that, but I could. Okay, okay. In fact, that's how I write it in my papers. So I'll still put a parenthesis around that just to be a little. Okay, and then e to the x root kappa, big X, root kappa little x, minus big X squared kappa t. Okay, so these are the Krauss operators of the diffusive measurement of a single observable. So I'm going to write it a slightly different way and then compare it to the Arthurs-Kelly Krauss the von Neumann Krauss operator. I realized, yeah, Rob, when we were talking about von Neumann measurement a couple classes ago, you were talking about von Neumann interactions. And I was also thinking about von Neumann rank 1 projectors. And I sort of realized watching back, maybe that's not what you had in mind, because you were asking about universal measurement. And you said anything that has von Neumann interaction.
Yeah, Hamiltonian is like P tensor A, reducing arbitrary operator. P translates meter.
Right. But that's not, I guess, what we usually mean by a von Neumann measurement. There, usually, you do think you have a Hermitian operator with rank 1 projectors. And like I thought projection onto the eigenbasis is usually what von Neumann measurement means.
Sure, and
so,
if you think of the measurement theory of a von Neumann measurement and say, oh, let me imagine the probe as a physical degree of freedom that's a unitary as a Hamiltonian, that's exactly this form, P tensor A, where A is observable.
Right. Yeah.
Yeah, that's usually called the volumetric threshold.
Okay. Cool. Okay, so we'll clarify that in a little bit too. So main thing to write here is, okay, so I'm going to define a new random variable, which is u equals x over root t. Okay. I'm going to do this because I want to compare this to the Arthurs-Kelly result. Okay. So u equals x over root t. So if I do that, and then I just write everything under the same square root, what you get is du over root 2 pi e to the minus half u minus 2 root kappa t observable x squared. Okay, so I'm going to compare this. Actually, I'm going to move my coordinate transformation. So if we do the so I'll call this diff now, diffusive. Okay, and I keep calling this Arthurs-Kelly. I'm trying not to. I'm trying to save Arthurs-Kelly for 2 observables. But now I'm just going to talk about 1 observable where you're not doing a diffusive interaction. So maybe I'll draw this picture again. Remember, these guys are a whole bunch of independent interactions. Okay, and then we sort of classically add up, if you will. Maybe. Oh gosh, I wasn't going to talk about this part yet, but maybe. So each one of these semicircles is a dw. Okay, and then this. let me draw this nicely. Okay, so I'm going to diagrammatically draw this thing as we've got our quantum system. And we've got all these meters with dt interactions, right? So
These little beam splitters with 2 output ports, like the V's. So most puzzles you draw a little V.
oh yeah.
Am I to think of that as there's a beam splitter?
No. It's just because I want more space. So I could just draw them like this. So I get a new meter prepared. So okay.
It's just another wire circuit.
Yeah, and it's got to bend just so I can. The interaction. Yeah. This is, I think of this as the unitary, and this is the meter, and this is the system. Okay, so then.
Implicitly, all these meters are prepared in products made of this very particular variety.
Yeah, these meters are independent. Yeah.
These coherent states that we talked about earlier. Check this using the ket 0.
Yes. My ket 0 almost always means like a vacuum. Yeah. Not a 0 position. Yep. Okay, and so then the point is each one of these, the outcome was, or the register was dw sub t. Okay. And so now part of what I'm trying to emphasize is notice for a little while we paid 0 attention to the system in the cross operator. We were just paying attention to this addition rule in the Wiener increments. Okay. So actually that addition rule could have been done by an automaton. Okay. So each one of these DWTs, I'm now imagining there's a classical memory. Okay, so double line means classical memory. And this is basically going to be my x. Okay. So every time I get an increment, I'm going to program this classical memory to update to x goes to x plus dwt. Okay. So then can you see this automaton will actually know what the Krauss operator is at the end, right? Okay. Do you guys, I feel this is, yeah, this part's important. You guys see how this rule could just be thought of classically? Yeah, good. Okay. So, yeah.
You would even need to have like a register that gets updated to the state. Take all the DWs, bring them together in some, right? Like I can think of it as a code.
Right.
That just acts on that set,
Right.
rather than sort of updating as you draw.
Yeah, but I guess part of what I'm saying is this is easy to do. It's, I guess, infinite amounts of memory, not so easy.
With the traces, you just be tracking.
Yes, exactly. And so part of what I emphasize when I talk about the instrumental group, so in that language, here the instrumental group is just the real line, is just this real random variable. And where you are in that group, you've sort of long forgotten. Once you're with that time-ordered exponential, you just forget what the system is. Yeah. And you're just doing these rules. So these update rules get much more complicated when there's multiple non-commuting observables, but they're still automatic, which means, yeah, and we'll talk about that soon. So this is me just reminding you guys where x comes from. Okay. Now, if we compare that to omega x von Neumann, so if I say omega x von Neumann is, just a quick reminder. Okay, so this one, x actually just means the register of a position measurement. Okay. And I'm going to use the same 2 sigma
Minus or a plus in there? T minus dt.
t minus dt, yeah. No, not plus, minus. Okay, so this is me just doing a von Neumann interaction. Oh! G, T. Looks like I've found the sweet angle. I'm going to write this again. Minus I 2 sigma over h bar p m tensor x. Okay, so this is a finite time coupling instead of a diffusive coupling. I'm putting the 2 there because the 2 is in my conventions for diffusive stuff. Okay, so that, of course, so if this is a Gaussian, right, then this is just dx over root 2 pi sigma squared.
So you said, what is it Gaussian?
The meter state, yeah. And the only thing we're changing is there's only one meter state now. It's being coupled for a finite amount of time, not infinitely many.
If the meter state is a coherent distribution with a certain Gaussian width over position sigma.
Yeah, yep. Yeah, and so then I draw those, right, as the 1 meter. No V's. Okay. minus x minus 2 sigma gt x squared divided by 2 sigma squared, which if I do a similar rule here, so now I'm going to do my standard Gaussian is just x over sigma. And I get standard Gaussian. Then okay. So the only thing, if I did this right, the only thing that's different, this is a u. The only thing that's different between these two is whether I get a gt or a root kappa t. So what is that saying? It's saying in the same amount of time, basically, your resolution hasn't spread out quite as much as if you did a von Neumann measurement. I guess, are we going to agree? We're going to call this a von Neumann measurement, okay? Because it's not two observables. So it's not Arthurs-Kelly yet. I'm calling this von Neumann. I'm calling that diffusive.
You could also, if you wanted a word, call it impulsive.
Impulsive?
Yes, in the sense that we're conceptualizing it as like an interaction, rather than maybe not impulsive. And often we don't talk about how long it takes to do the measurement.
Mm-hmm.
Say, it's a strong measurement, it happens, it's over,
Mm-hmm.
and as opposed to thinking of it as proceeding
Right.
over time.
Yeah. So,
Maybe impulsive is not a great word because you're
Yeah.
thinking of it as actually taking time, capital T.
yes. And, yeah.
Yeah, I understand what you mean.
You've got stroboscopic and stochastic.
Yeah, this is definitely stochastic. I thought people mean this when they say stroboscopic. Yeah, people who use the word stroboscopic, I don't understand what they're saying, and I don't like the word. But
Okay, that's
I don't know. Yeah. So,
intermittent. Valuity.
I don't know. So, of course, I don't mean projectors onto eigenstates. And this is part of what we were talking about earlier. I would call this a universal measurement, just like that one. Of course, the behavior in time is different. And then something else to emphasize is you can't really see anything happening until you give X a spectrum. There's sort of, even though these are correct statements, for example, I can't tell you when the measurement is over, right? Because the measurement, like I need to know what the smallest eigenvalue spacing is before I can see that the Krauss operators actually, look like this. And without that, so these are like right? I need to give this thing a spectrum.
Sorry, you said something like you don't know when the measurement is
Is over, yeah. So, yes. So I think we need to move on to the second example, where then it is obvious the measurement is over. Okay.
Yeah, a comment.
Yeah.
Over on the right here, we're imagining that a certain unitary interaction takes place for a specific interval.
Yep.
And then it's done. So it's sort of clear when the measurement's over here.
Mm-hmm.
It's only for the diffusive case where you'd say, well, we've got these traces. But couldn't then I say, well, I'm just going to go up to time capital T, and then I'm going to just compute and the measurements, I declare it to be over at time capital T, and I just say, what's the effective measurement? Yeah?
Right. Yeah. And
So,
yeah.
why do you say this? Yeah, I'm not following this.
Interesting. Yeah. So we need to talk about the second example, where what's going to happen is the addition rule is actually going to get an exponential in it. So that signifies that after some time, doing more measurement doesn't actually change the POVM. So that's the case in like Howard Wiseman's measurement. So there's this feature that comes from the non-commutativity that actually shows you're not collecting more information. Your POVM is not evolving anymore.
Whereas here it is.
It is, yeah. There's still all of this. There's no, yeah.
Okay, before you move on, so if I went and calculate the POVM that this is measuring,
Yeah.
am I right in
These-
thinking it is going to be still all the POVM are going to be diagonal in the eigenbasis of x?
Sure, yeah.
So it's just a noisy measurement of x ultimately. Again,
Maybe.
that's just language, but if I have a projector value measure, and then I say, well, rather than those projectors, I have noisy versions of them.
Maybe.
Projectors, whose mean coincides with the corresponding projector. So like if that were a position operator, rather than having a measurement that tells me precisely the position, I might have a measurement these elements are Gaussians.
Yeah.
The means correspond to the different positions.
Yep. Yeah, and in fact, this makes perfect sense even if x is a position measurement, or if is a position
It
observable.
would be the measurement I just described. That basically saying
Yes.
it's a coherent state POVM where the means of those coherent states reflect the different possible.
Right. But at no point do these become projectors onto position because position eigenstates are pathological. Like,
Sure, but
it-
in the limit,
there's nothing to limit to.
I can make it arbitrary. Like if I think of squeeze states, I can make the variance in position go smaller and smaller. Yes.
That's true. But then, so versus like if the spectrum of x is discrete, then there comes a point when these operators have no overlap. That discreteness in the spectrum, you can sort of say when you're done measuring. Versus like if it's a continuum of spectra, there's actually never a resolution. There's never a time when there's no noise. Like this doesn't collapse to a von Neumann projector unless X has a discrete spectrum.
If X is a discrete spectrum, given that your meter starts out in a coherent state, and a fixed translation of that coherent state is never perfectly distinguishable from the original coherent state itself, it seems to me you're still always going to get a POVM that is not a projector value measure. You're still going to have overlap between the elements of the POVM's elements. So I would say it feels to me like the continuous nature of your meter system means that you will never achieve the ideal of projectiveness, and that is independent of whether the observable you're measuring has a discrete or continuous spectrum. It's more about the nature of the meter.
Okay, sounds like we need to plug in, like if X has a spectrum, if X has a discrete spectrum,
That line you're drawing
is the
is
line of
the
use.
position coordinate of the meter degree of freedom.
Yeah,
That is continuous, and it's
absolutely,
relevant whether the system is finite dimensional or infinite dimensional. We're talking about the meter. That
absolutely, yeah.
it starts out in a coherent state which has support everywhere. And all that ever happens to it in response to the system degrees of freedom is it gets translated. You will never be able
And it gets, that's what this is. So, like this is saying that the resolution between the eigenvalues of X is getting higher and higher. These are becoming more exclusive, mutually exclusive. So, yeah. Let's see. So before I write this down, is it clear all of this is universal? Has nothing to do with the spectrum. Okay. But now I want to talk about when there is, so like if X had a spectrum, X sub lambda pi lambda, then these are all the POVMs are a bunch of Gaussians that are separated. So I'm going to write this on a different board. Okay, I'm going to erase this. It's like in the Stern-Gerlach, for example, right? So that one's not diffusive. That one projects onto von Neumann. And you know that once the spreading out is larger than the beam width, basically, you have a von Neumann projection. Right.
Well, what I would say is you never achieve the idealization of a projective measurement. But it is true that the deviation from that is exponentially suppressed. Right?
It's exponentially suppressed when the spectrum is discrete because of that finite, right? Otherwise, there's like equally, if there's eigenstates that are infinitesimally close to each other, there's no von Neumann measurement ever.
Yeah, in some respects, there never was an ideal of projective measurement in nature.
Yeah, it's a feature, not a bug. You shouldn't get a position von Neumann measurement because it doesn't exist. Right, yeah. But you should get angular momentum von Neumann measurements to good approximation. Yeah.
But if I, for example, define, say my system is continuous, and rather than defining, the position measurement,
Yeah.
I say I'm going to take a bin size. I'm going to say I want to measure position up to bin size delta x.
Yeah.
Well, now I have a discrete set of eigenvalues, and exactly the same comments will apply. That I can approximate the projective measurement into these bins up to exponential suppression. Yes.
I agree. Okay, so it sounds like that was taken care of. So now, I want to talk about Howard's measurement. Okay. So now we're going to do example 2. So L equals A over root 2 minus IA over root 2. These root 2's are just going to be convention, okay? So first thing to think about, right, is that quadratic term. Okay. And you guys see the main thing that changes, if I only did A and not minus IA, I would get this L squared term, right? But if I do A and IA, then the L squared terms are actually going to cancel. So that's actually why this ends up doing the coherent state measurement. So this says that QL is in fact just half A dagger A. Okay. There's another half because I put these root 2's in. Okay, so then the time-ordered exponentials we get.
What I'm supposed to understand yet is why this measures the coherence of the right?
No, we'll conclude that in a moment. Yep.
Yeah, you make the connection to x. sort of like X didn't show up here.
There's no X, yeah. And in this case, you get a complex plane. So we'll get there in just a moment.
We're gonna just remind
Oh, sure.
of QL line class.
QL was just X squared. Oh, did I erase the wrong? Oh, it's right here. Okay.
Okay. So, got it. All right. Yeah, thanks.
Cool. Okay. So QL is that, and our Krauss operators are. So I'm going to accommodate things a little bit. So I'm going to define the complex Wiener increment to be, so I'm going to call the outcome of this one, so I'll start writing the Krauss operator too. So omega sub d omega is, so this is just a weak one for a moment, d mu of dw q d mu of dw p e to the a root kappa dw q minus ia. Oops. I'm doing these root 2's right. Sorry. Okay, does everybody believe that is the weak Gaussian Krauss operator for the two Lindblad operators A and minus IA over root 2? So these are just the L's, and then I'm giving the Wiener increment for each of them a name, Q and P, because the Hermitian part of this is Q, and the Hermitian part of this is P. Okay. So the tradition in optics is to write all of these Q and P bits as a complex amplitude. Okay. So in fact, that root 2 is conventional, which is why I put this root 2 here. That's just what we do in optics. So if I write everything in terms of that, then the first guy we just write as d omega. Okay, so this now means a complex Gaussian measure. Sorry. So we need square root of measures all the time. Okay, and then this thing is d2 d omega over pi dt e to the minus d omega squared over dt. Okay. The factor of 2 got absorbed into the complex Wiener increment. E to the, so now this guy I can just write as a root kappa d omega complex conjugate. Okay. Is everybody okay with that? So the real and imaginary parts can be thought of as two Wiener increments corresponding to two different Lindblad operators.
I'm trying to follow that. You're just combining the DWQ and DWP together like you did down there.
Yeah.
But you don't have an I difference.
Well, the I is now in here. Yeah, I can now move this eye over here.
I see.
Oh, there is an eye, yes. Sorry.
Okay, and why do we have that omega star down here? You just called it omega.
Oh, because there's a minus sign right here.
Oh, I see. Star here is almost negation.
Yep.
And you drop the T.
I don't have a T on this one, but I could put T's on everything. Yeah. Okay. So this is the weak Gaussian Krauss operator of indirect heterodyne. I'm telling you guys that indirect heterodyne boils down to just this, and then we're just seeing the consequence of that.
I was going to ask about,
Yeah.
so from my knowledge of quantum optics, I would expect that POVM that ultimately gets defined,
Yeah.
if it's going to be associated with coherent state measurement, it's going to be projectors onto coherent states, which are going to be like time orderings of exponentiations of state minus alpha, state dagger minus alpha star. Is that kind of like the endpoint for this whole derivation? Like that's when you say this is going to be coherent state?
Yeah, we're just going to do the time-ordered exponential, and sure enough, this A dagger A is going to turn into a projector on the vacuum, and this information is going to be the coherent POVM amplitude. Yeah.
It's going to be coherent state POVM is like a Luder's update. Is that right?
No. Yeah, so these are not, so that's a good point. These, even at order dt, are not Luders, right? That's not a Hermitian-Krauss operator. It's, yeah. In fact, they're not Luders because this measurement always leaves the system in vacuum.
But I guess I'm referring to like the effective measurement, like you did before, when you said, okay, well, let's lump together all the Krauss operators that are the same with the effective measurement. That too will not be Luders. Correct?
Yeah, that's right. Yeah, this is very not
In your
Luders.
last example, example one.
Yeah.
It was Luders?
Yeah, yeah.
Okay, so now the example
Because everything-
Like example one, insofar as it's not a Luders update.
Not even weakly, yeah. Yeah. It even turns out in, so here, or in the single observable, the weak measurement was Luders, and the finite time measurement was also Luders, because everything commuted. Okay? But in general, even when it's weakly Luders, it's not Luders in finite time because of the non-commutativity. Yeah, and in fact, that way that the Luders measurement becomes non-Luders, that's the same thing as curvature. Yeah, POVM curvature. Yeah, all kinds of stuff here. This one turns out to be curvature-free, which is why it's easy to do. Yeah, POVM curvature-free. But I'm getting ahead of myself. Okay, so is everybody convinced that if you just plug in these two Lindblad operators and you write things a little bit in terms of complex Wiener increments, then these are the weak Krauss operators? Great. Okay. So now we just need to calculate the time-ordered exponential. So I'm going to erase the... Do you guys have this in your head? QL is probably the most important one. It's, yeah. We don't have much more time anyway, so we'll just do the second example. Okay, let's see if I can hit the time-ordered.
This is being recorded today. We just don't have anybody online. So.
Right. Yeah. Kevin is celebrating American Thanksgiving. And I don't know what happened to Yuja. Maybe Yuja's with us. Oh, hi. Okay. Okay, so I just need to transcribe something, and then we'll crank them out. So I'll just write this backwards a little bit. So omega sub d, omega 0 to t. Again, that's just going to be square root Wiener measure, the omega 0 to t time-ordered exponential. This guy. 0 t minus a root kappa d omega t star minus half a dagger a kappa dt. Okay. So this is not hard. I'm not going to bother with the measure part. I'm just going to talk about what these exponentials look like. Okay. So the main thing to notice is there isn't a whole lot of non-commutativity around, right? The only non-commutativity is that this doesn't commute with this. Okay. So remember, this is just a product of a whole bunch of exponentials. So in the end, all we really have to do is know how to we're going to keep getting a bunch of terms that look like okay, let me just write this out. What is the best way to describe this? Okay, so I just zoom in on this bit. Okay, so that's going to be, you know, okay, I'm going why is this part confusing me? Okay. Okay, so I'm saying that all we really need to know is how to commute these guys. Okay, so we're going to have a bunch of commutation relations that are basically this guy is going to end up just being kappa t, but we're going to have to keep passing these guys through. So I guess I'm going to show this is just integral a root kappa integral 0 to t minus d omega t star e to the minus half kappa t e to the every time. And then the exponentials on the left. Okay, so I'm trying to explain to you guys why the time-ordered exponential is just that. Okay. And it's basically because, think about taking this and then incrementing it by another dt. So I multiply another one of these over here. Basically, all I need to do to get it back in this form is to commute this part over this bit. Okay, so that's what I'm saying over here is you always end up with, in the next t, a d omega t star, and we want to move it over to the other side. Okay. So if we do that, of course, that's just the same thing as, the nice thing about exponentials, right, is I can, conjugation commutes with exponentiation. Does everybody see that? So, yeah. Right. Like I'm using e to the x, e to the A. So I've got something like this, and then I'm going to multiply the left like this, and then this guy. Conjugation commutes with exponentiation. Yeah. It's like if I think of this as a Taylor series, I can just keep sticking in a bunch of e to the x. So this is true even for A analytic, right? E to the x, f of A, e to the minus x. That's just f of e to the x, A, e to the minus x. Because once it's analytic, then this is just powers of A, and between all of the powers of A. Yeah, yeah. And in fact, this is part of the definition of the fundamental group. So this fact that conjugation commutes with exponentiation is a topological statement. It's basically that if I move this arrow over, I'm not going to go there. Yeah. It's a big deal. Yeah. Okay, so are you happy with that now? Okay. And then that is not hard to do, right? Because the commutator of A dagger A with A is just minus A. Okay, so then this thing is just e to the minus half, A dagger A, kappa T, e to the A, d omega T star, e to the minus half, kappa T. Sorry, Mike. This part just comes along for the ride. And then this is me doing the conjugation of A. You guys remember like e to the x, A, e to the minus x. That's e to the add x of A. So, because A is basically an adjoint eigenvector, I can think of this as add A dagger A of A. Okay. Then, yeah, this thing is an eigenoperator of this. I need another T here. Is there any, you guys good? Okay. Yeah, sorry. So what I'm saying is this time-ordered exponential is just this. And then this is the feature I was talking about earlier, that actually it's clear that the measurement stops after some time, because basically this thing means the POVM stops listening. It doesn't, if you take t to infinity, this is saying only the Wiener increments up to this time 1 over kappa actually contribute to the POVM, right? Yeah, so that's interesting. So then maybe you can see now, in the limit that t goes large, this becomes a projector onto vacuum. Okay. And then, so I'll write that out. So again, this is universal, but now if we assume that A dagger A has the usual quantum spectrum, kappa T large, A dagger A is the usual Ni, projector on Ni, N. This becomes projector on the vacuum, and then this e to the A alpha, or alpha of the record is, oh, I think I found it. Stop. Is this guy. Okay. So the addition rule is a bit different from the single observable, right? The non-commutativity is actually shutting down the POVM after some time, which is a new feature. Oh my gosh. Okay. So I think that's it for today. Yeah. Are there any questions?
Is there some intuitive way of understanding this new feature?
I don't know. It comes from the non-commutativity. Like one way I would say it is the group is not a commutative group. These time-ordered exponentials live in a three-dimensional non-commutative group. And this is the kind of stuff you get in general, these modified addition rules. So you don't get regular Wiener increment addition because the group isn't commutative. The group is actually what's telling you how to add up your Wiener increments. And so this is saying you add them up differently. And it's because the instrumental group is not commutative. Because if this is a commutative addition rule, right? Anything that's not this is a non-commutative addition rule. Yeah. And that non-commutativity is coming from just how the quadratic terms of the diffusive measurements interact with the linear terms. Yeah. So that quadratic term is because of its transformation structure decaying the linear term. Yeah.
I wonder if it has something to do with the fact that this back action between here and the system. So if I'm coupling by two different types of observables, and maybe once the back action piles up, I can kind of expect diminishing returns in terms of how much information I can get about it.
How do you separate like unitary back action? Yeah, there's positive back action, and then there's unitary back action. And
I think what positive back action is.
yeah. So it's not unitary back action. So like if we chose,
Oh, you mean like one that you apply yourself?
yeah, like would you say any Krauss operator is a back action?
No, I guess what I had in mind is something like, even if I go to a von Neumann coupling, like Arthur's coupling, I have a von Neumann type coupling, but now I have two probes and different observables, A and B, that don't compete. Well, just the coupling necessarily involves, so that observable A tells me not only how the probe translates, but also it tells me a little bit about how the system suffers back action. And so if A and B don't commute, that means that the system is going to be suffering back actions.
More back. Okay.
That disturb the other observable.
I guess so.
Like over time,
Yeah.
you get a lot of information about the original
Yes.
value.
Yes. And there is some wiggle room there. Like here, the back action is that you always end up in the vacuum. Or that's part of it. The post-measurement state is always in vacuum because that's how this back action works. And somehow that's the same thing as saying the POVM stops listening. But those are two different sides of the Krauss operator. And is it all back action? I don't know.
All right, we'll continue this.
To be continued, yeah. Thanks, Rob.
So this was a never stop.
What?
This way you use for long time you always get more information.
Well, like if X has a discrete spectrum,
Okay.
then no, right? At some point you already know which eigenvalue was selected.
How about
Yeah, the big thing is this distinction between the POVM and the post-measurement state.
Yeah.
And so POVM attenuation, yeah,
attenuating POVM because it's not the stimulator?
yeah. Because it's not a post-measurement effect.
Yeah.
Yeah, thank you guys.